Mm-hmm. Well, after this, we have 2 more lessons. We have 2 lessons in Chapter 9 we need to do. Okay, so we ready? You guys back there ready? Try a quick little graph here. So far, when we've been thinking about graphs, specifically on a rectangular plane, an XY plane, we've been looking at points that can be described using an X and a Y value. Yeah. No, not really. We're going to stay with rectangular graphs in this section. What a parametric equation does is it introduces a parameter. So in this case, the parameter is t. And in most cases that you will see parametric equations, t usually stands for time. So it doesn't have to, but in most cases, especially in physics, it'll stand for time. So now we also have to describe not only the location of these points, but also what time they occur. So you need to think about not individual points on a graph, but you need to think about, let me actually erase this. Think about one point that moves along a path, and it traces a graph as time moves forward. Does that make sense? So for example, if this is where time equals 1, the point's right here. What if another second elapses? That point would move up to here. And then as one more second passes, that point would move over to here. And as time moves on, that point starts to trace a curve. Okay? So rather than thinking about this curve as a collection of XY points, you think about this curve as the path of a point that moves as time transpires. Does that make sense? So the parameter is t, and depending on the value of t, we're able to find the specific location of a point. Okay? So it still graphs things like we're used to on a rectangular plane, but rather than graphing the entire graph at one time, we have to choose individual points depending on the value of time, or t. So for example, well, let's write down a formal definition before we do an example. Here's parametric equations, formal definition. If f and g are functions defined on an interval I, that just means they're functions whose domain belongs to I. So their domain doesn't have to be all real numbers. It could be restricted to an interval. Then the set of points f of t comma g of t is called a plane curve Now, all that is a fancy name for a graph that's produced using parametric equations. A plane curve is a graph that you graph by letting t equal specific numbers, finding the x and y values, and plotting that graph. That's called a plane curve. The equation or equations, plural, x equals f of t, y equals g of t, where t belongs to I. I know it's getting a little complicated, so let's slow down a minute here. What is I? What the heck is I? The interval for what? The domain of the functions, right? So t also must reside in that domain of the functions f and g. So t belongs to I. Our parametric, so these two equations right here, x equals f of t and y equals g of t, are what are called the parametric equations. So parametric equation comes in pairs. You have to have an equation that gives you an x coordinate, and you have to have a separate equation that gives you a y coordinate. You put them together to start to form your plane curve for different values of t. And t is called the parameter. So that's an abstract definition with a lot of funky words. Let's get a little more concrete with an example here. Example 1, sketch the plane curve, which really just means use the parametric equations to make a graph. So x is equal to t squared minus 3t y is equal to t minus 1. Just think for a moment at those two. How are they defined? What's the domain? X equals t squared minus 3t. Are there any restrictions on what t can be? What is that, by the way? T squared minus 3t. What kind of graph is that? It's a parabola. What's the domain of a parabola? All real numbers. What about the other one? Y equals t minus 1. That's a line. What's the domain of that? All real numbers. So our interval is all real numbers. That means t can also be anything. When we're starting to choose values of t, t can be any real number. Essentially, that means t could be negative or positive. So here's what you do. Or here's one thing you could do. Here's what I would recommend that you do. We need to have a column for t. And we're going to choose the values of t because t is the parameter. We can choose whatever we want for t. But the values of x and y are dependent on what we have chosen for t. So x is equal to t squared minus 3t, and y is equal to t minus 1. So to sketch a plane curve, we need to have coordinate points x comma y. So where are we going to get a number here and a number here from? What do we do to get a number here and here to get an xy coordinate? Choosing random numbers for t. So since t can be anything, let's include negatives and positives. Let's do negative 2, negative 1, 0, 1, and 2. Just to get a few points that we can plot. Remember, what we're doing here is not imagining a graph that's a collection of points. We're imagining a point itself that moves along the plane, sketching a graph as t increases or decreases. So if t equals negative 2, this is simple stuff, you guys. Do this in your head. We get 10. For x, what do we get for y? Okay, so there's our first xy coordinate pair. What about negative 1? Let's see, x, that's going to be 4, yeah. And negative 2. And for 0? 0, negative 1. We're clear on where these numbers are coming from. These aren't just randomly chosen numbers here. These are randomly chosen numbers for t. I chose these. But these have to come from the parametric equations. What about when t equals 1? We get negative 2 comma 0. And when t equals 2? Let's see what that looks like. So 10 comma negative 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's where the point would be when t equals negative 2. There's where the point would be. T equals negative 1. It's kind of hard to tell what this is going to trace just using the parametric equations until you've actually graphed it. Because just using these 3 points, what is this looking like? Maybe a straight line. It's kind of hard to tell. That's why we need to have more than just a few points on here. So when time equals 1, or when t equals 1, we don't know if this is time necessarily. So far we have this. We need to get a few more values of t. Because what happens after this, do you think? It's not a function in terms of x, no, but it's okay. These could be circles, sideways parabolas, they could be spirals like this that spiral around. There's a whole bunch of funky things that could happen here. What do we think happens after, this is where t equals 2. Does it go straight up? What do you think? You think it might curve around? Let's do one more quick value of t. T equals 3. What are we getting here? When t equals 3, 0, yep, 0 for x. And let's see, so it looks like we're going to get a 2. So 0. So it starts to come back around. So it's a sideways parabola, and we're not going to extend this to the right because we don't have any more points for t. Remember, this is not really a collection of points. It's whatever points we've graphed as t increases. So we can stop there on that one. That's what I would recommend that you do when you're sketching a plane curve of parametric equations. Make a little table like that, choose some values for t, use the parametric equations to find values of x and y, graph it on the coordinate plane there. Now use the same example. Let's make a part B. We're going to get into the second objective here. It would have been much easier to visualize what this graph would have been had we known the rectangular equation instead of the parametric equations. So what we're going to do is eliminate the parameter. This will be the last example, then we're going to have to get out of here. Eliminate the parameter to find the rectangular equation. So right now all we have is a pair of parametric equations. X was equal to t squared minus 3t, and y was equal to, what, t minus 1? Or is it t minus 2? Here, t minus 1. So here's some guidelines. Choose the easier equation and solve for t. most of the time there's going to be an obvious choice, like this one here. Which would be the easier equation to solve for t? The y one. That's an obvious choice here. So this is going to be, so if we have y equals t minus 1, what does t equal? T equals y plus 1. Okay, once you've done that, then you substitute the value of t into the other equation. You can't substitute back into the equation you just used. So we're going to take t equals y plus 1, and we're going to substitute that into the x equation now. You guys follow? So x is now going to equal, instead of t squared minus 3t, that's going to be y plus 1 squared minus 3 parenthesis y plus 1. And cleaning this up a little bit, we get x equals y squared plus 2y plus 1 minus 3y. What am I doing here? Just getting rid of the parentheses by distributing and squaring that binomial y plus 1. Are we okay? I know I'm going kind of quick. Are we okay on what happened there? And what would you suggest now? Combine the like terms. Yep. X equals y squared minus y. Let's see. Wait a minute. Y squared minus y minus 2. We're actually just going to leave it like this for right now because the bell's going to ring. But anyway, just for a quick second. Everybody stop for a second. We did talk about this back in our 1050 days. If you only have one variable being squared and the other one isn't squared, what kind of conic section is that? If one of them's being squared and the other one isn't? It's a parabola. If both of them are being squared, if x and y are both squared, it's either an ellipse or hyperbola. And if the y is squared and the x isn't, do you remember what kind of parabola that was? It was a sideways parabola, and isn't that what we graphed here? A sideways parabola? So anyway. They are super simple questions.